Hey everyone, welcome back. This is the final installment of my course overview of Materials 2D03, Thermodynamics of Alloys and Phase Diagrams. My name is Josh. I'm a second year's material engineering student at the University of McMaster. And yeah, let's get right into things. We left off talking about activity and different activity charts. Now what we're going to be doing is we're going to be doing some examples along with talking about solid mixtures and solid solutions. So first off, solid mixtures, they are miscible, fully mixable, which means there's no miscibility gap. They're mixed phases. There is only one phase. Next, solid mixtures, they have the same crystal structure. They have similar atomic size, and they have similar valence and electronegativity. Now going on to solid solutions. There are three types of solid solutions to consider. One, an ideal solid solution has random mixing and enthalpy equal to zero. A negative deviated solid solution has ordering of the mixing with an enthalpy of less than zero. And a positively deviated solid solution has clustering of like particles with an enthalpy greater than zero. Going on here, this is straight from the lecture slides that was worked off in the class that I was in pertaining to this course. Now, what we did in this course was we analyzed different phase diagrams and made Gibbs free energy curves of them. So instead of drawing them and going through that lengthy long process, we're just going to be going over why each diagram looks like how it does. So this first one we're going to exhibit has three different parts, three different phase diagrams. Right here, or sorry, not three different phase diagrams, three different Gibbs free energy curves. Right here at the T1, we have all liquid, which means the liquid curve must be underneath the solid curve. And that's exactly what we see. When we go down to the melting point of A, so if we are at all A, completely at A here, when we reach this point, this is the melting point here. At the melting point of A, we begin to see some crossover from the solid and liquid part. At T2, we have some part where we have a liquid, where the liquid curve is less than the solid curve. Then we have a common tangent between the solid and liquid curve because they are both in the same phase at the same time. Then our solid curve goes below our liquid curve for the remainder, just like that. At the melting point of B, down here, this is when the B line starts to uncross. And at this point of uncrossing, we have at T3, one solid region. Cool. Let's go over to our next example. So at T1, we have the liquid line being lower than all of the solid line. So we are in a totally liquid phase. And if we want to know where or which solid A or B has the higher melting point, we can see at T1, the distance between the solid and the liquid line is less than the distance between the solid and the liquid line of B. So we can say A must have a higher melting point because its distance from the solid line, or sorry, from the liquid line is lower. It's less removed from the liquid line, so it's going to have a higher melting temperature. Moving on to T2, I see we have some fully solid. Then we have a phase where we are in equilibrium with the liquid. Then we have a fully liquid phase for a little bit. Then we are in equilibrium with another solid. And then here we have a fully solid phase. And that checks out. Solid, equilibrium, liquid, equilibrium, solid. And here I see we have a solid phase, then we have some equilibrium, and then another solid phase. Solid, equilibrium, solid. Moving on to this last one, we see when we increase the miscibility gap, if our miscibility gap gets increased, it will converge with the liquid line and make a eutectic point, which is what happens here. We can see here, since we have two different lines for our solids, alpha and beta, we know that our A and B have different crystal structures. Now here, I see at T1, we must have just a tiny bit of A, and then an equilibrium, and then all liquid. T2, we have a little bit more of A, we have an equilibrium, we have a tiny bit of liquid, we have an equilibrium, and then we have B. At T3, we have A, then we have an equilibrium between all three at the same time, then we have B. If we have equilibrium between all three, this is what we can call a eutectic point. And then at T4, I see I have A, I have an equilibrium between A and B, and then I have B. And that all makes sense, according to this chart. Now, at a certain temperature, let's draw our own Gibbs free energy curve. So I see we're working with T2 here. I'm going to draw alpha in green. I'm going to draw liquid in blue. And I'm going to draw beta in purple. I can see that there's a point where I have all alpha. All right, so I can see I have a point where I have all alpha right around here, right? This can be my alpha line. Then I have a point where my liquid line and my alpha line have a common tangent. Around there. From here, there's a point where I only have liquid. Then my liquid and my beta are going to have a common tangent. And that common tangent should go till around there. See if I made it well enough. That's fine. These common tangents can be hard to draw sometimes. That common tangent is good until around there. And then I'm going to have all beta. So alpha is the lowest. If I'm walking across the lowest line, alpha is the lowest. Then I have my common tangent. Then liquid's the lowest. Then I have my common tangent. And then I have my beta. Perfect. Now, let's do something exciting and let's draw the Gibbs free energy curve. I'm going to grab this. I'm going to delete the boxes and the lines. All right. This is going to be interesting. So I'm going to start with all alpha up here. And alpha is green. I start with all alpha up here. And I start with all beta up here. We're going to draw Gibbs free energy curves for alpha and beta. Since our alpha and beta form two mixtures, or two solid mixtures, we can say that these solid mixtures have positive deviation. This is just something that we're going to claim. We also have to claim, this is going to make us a lot easier, that the liquid is ideal. Now we have to state standard states for both alpha and beta. for both A and B. We know since A starts as a solid and B starts as a solid, we can say A and B both have standard states of solids. So let's go with the A curve. We have some positive deviation right to start with. Then we have a constant path. Then from here, we have ideal behavior. We have another constant path. And then we have to go all the way to 0 because we have 0, A. Let's draw beta. I'm going to start with some positive deviation, then a constant path. Then I'm going to have ideal behavior along with another constant path, followed with leading to 0. Cool. Now you can see all my solid points have positive deviation for both. If I were to draw the ideal lines, positive deviation, positive deviation. Cool. All right. From here, we're going to move on to a new topic. We're almost at the end, which is fantastic. We're going to be talking about intermetallics. Now, we get intermetallics when A and B have different crystal structures, and a new crystal that has a different structure from both forms. This intermetallic crystal structure has a very low stability, meaning it will have a narrow Gibbs free energy term, or Gibbs free energy curve. If we were to draw this, we can say if we were to have alpha, beta, and gamma, we were to have alpha look like this, beta look like this, and gamma look like this. Actually, beta is going to be narrow and in the middle, and then gamma is going to look like this. We can see that beta is the intermetallic because it's in between the gamma and alpha ends. And we can draw, just practicing this stuff. Boom, we have a comet tangent there. And we might, I'll draw it. So we have a comet tangent with this one. Maybe we'll get it looking like this. Something like that, we'll say maybe. I don't know. Anyways, we'll have it look like this. Boom, like that, right? We know beta is our intermetallic because it's in between the two. These are just some loose ends we're going to pick up now. What's a peritectic? A peritectic point. That is when we go from a liquid plus some solid to one solid. Let's talk about solubility. Solubility is the measure of how well something can mix. if we go up here, we'll look right here. We can say that at this point, alpha has, sorry, this is the point where B is the most soluble in A, right? The highest point where we can have the highest mole fraction of B in a rich A solution, highly soluble point. This is a less soluble point because we can have less B in A. In terms of Gibbs free energy curves, the more narrow my Gibbs free energy curve, the less soluble it is. So if I were to have a Gibbs free energy curve looking like this would be a very soluble phase. If it looked like this, it would be a very non-soluble phase, which means I can't have a lot of B in it. So with that, what do we say about intermetallics? Well, it can be said that they are not very soluble. Now, the equation we can use in which measures this is this kind of equation, which I don't think we will be asked too much about, but just have that in the back of your head. All right, the very last thing that we're going to be talking about is microstructures. Now, if we have something growing inside a matrix of alpha, this is what happens in a phase transformation. We have a matrix full of alpha, but then we see what happens is we have a little bit, I'll draw this in a red circle. We have some growing beta, and we're going to keep it as a circle. Now, in order for this beta to grow, it has to apply some pressure outwards onto the alpha region because it wants to grow. The alpha region is going to push back with some pressure of its own. Now, this change in pressure is equal to times the surface energy divided by the radius, or the pressure that beta is pushing with is equal to the pressure of alpha that is pushing plus 2 times the surface energy divided by the radius. Now, this equation called the Gibbs-Thompson relates the increase of Gibbs free energy. The Gibbs free energy is equal to 2 times gamma times the volume, the molar volume of mixing for beta divided by the radius. What this does is in a Gibbs free energy curve, it brings up the Gibbs free energy. Let me grab my note for this super quickly. Sorry about that. So what this means is if we were to have a Gibbs free energy curve here, since we have some kind of radius associated with our new beta phase and some surface energy, our curve is going to be up here. And we're going to have an increasing line that looks like this, associated with this phase change. Before we end, I want to go back to this graph and just make note of one special thing here. We see that the alpha curve here is going to go up, 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 and when it reaches all of B, it is up here. Now, what does this value mean? This value, we know A and B have different crystal structures because we have different alpha and beta curves. This point here is the Gibbs free energy of mixing, if our beta particles or beta atoms or our B atoms assumes the alpha crystal structure. And up here, if we follow the beta curve, up here is if our A atoms were in the B crystal. And with all that, that's everything I wanted to go over in terms of this course. I hope you all enjoyed. I hope you all liked this review session. Thanks for watching, and I'll see everyone later.